Take a moment to think about infinity. Are there more numbers strictly between 0 and 1 than there are whole numbers from 1 to infinity? Both lists never end, but our intuition suggests the decimals are somehow packed tighter. To find out, we have to look at how mathematicians compare the sizes of infinite sets. The standard method is to see if we can create a perfect one-to-one correspondence, pairing every item in one set with exactly one item in another, leaving nothing out. As detailed here in Chapter 2 of Walter Rudin's Principles of Mathematical Analysis, we define a set as countable if its elements can be put into a one-to-one correspondence with the natural numbers, 1, 2, 3, and so on. If a set is too large for this pairing, it is uncountable. Proving an infinite set is countable requires us to find a systematic way to organize it into a single, comprehensive sequence. If we list it out, step by step, without missing a single element, it is countable. Let's test this on the integers. The set of all integers stretches out forever in two directions, negative infinity and positive infinity. By contrast, the natural numbers only stretch in one direction. It seems obvious the integers would be a larger set, but we can arrange them. We can start our list at 0 and then alternate, positive 1, negative 1, positive 2, negative 2. We assign the first natural number to 0, the second to 1, the third to negative 1, and so forth. Looking at this text from Rudin, we see the formal, explicit formula for this exact arrangement. We map the even natural numbers to the positive integers and the odd natural numbers to the negative integers and 0. The fact that the integers stretch infinitely in two directions doesn't matter, because we found an exhaustive path to visit every single number. The set of all integers is exactly the same size as the natural numbers. They are countable. We can step up the complexity. What happens if we had an infinite number of infinite sets? According to Theorem 2.12, a countable union of countable sets is still countable. This array from the text shows the proof. By following these zigzag arrows, we sweep diagonally through the infinite 2D grid, ensuring every element is reached. We apply this exact logic to rational fractions, placing them sequentially in rows. Try tracing it yourself. If you follow the diagonal path, you will systematically list 1 over 1, 2 over 1, 1 over 2, and eventually cross through every possible positive fraction. Fractions feel incredibly dense. Between any two whole numbers, there are infinite fractions. Yet because we can fold them neatly into this 2D grid and weave a single line through them, the set of all fractions is countable. But the countability streak breaks at Theorem 2.14. The set of all sequences of zeros and ones is uncountable. We prove this by contradiction. Let's assume we can actually write them all in a complete numbered list. The mathematician George Cantor devised a brilliant way to test this assumption. Cantor constructs a brand new sequence using the list itself. He takes the first digit of the first sequence and flips it. If it's a 0, he makes it a 1. Then he takes the second digit of the second sequence and flips it. The third digit of the third, flipped. He continues this forever. Here is the inescapable trap. We ask, is this new sequence anywhere on our master list? It can't be the first sequence because the first digit is different. It can't be the second sequence because the second digit is different. It differs from every single sequence on the list in at least one place. Because this new sequence cannot exist on the list, our initial assumption was wrong. The list is incomplete. You cannot put these sequences into a one-to-one correspondence with the natural numbers. The set is uncountable. Every sequence of zeros and ones can be mapped to a binary decimal. Therefore, Cantor's logic directly proves that the continuous real number line itself is an uncountable set. We can list out the natural numbers, the integers, and even the infinitely dense rational fractions. They are all countable. But the continuous real numbers and the binary sequences belong to a different category entirely. The continuum of real numbers represents a heavier, larger infinity than the set of fractions. There are mathematical gaps that counting simply cannot cross. To continue building your rigorous foundation in mathematics, subscribe to the channel. We'll keep working step by step through the core principles of analysis. See you in the next proof.